Okay. We will move to Mr. Sunil Kumar Gowda. He will talk about mud motors.
Hello. Yeah, everybody can hear me. Hello.
Yes.
Yes. Okay. So let me introduce myself first. I'm Sunil Kumar Gowda. For mud logging department with Schlumberger. Most of the time, I have worked in sub-Saharan African countries, like mostly onshore, offshore, and deepwater environment. I have very keen interest in well placement and geosteering. Thanks, Dr. Wael, for your lesson yesterday. It was very mud motor. So let me go through just a second, please. So everybody can see my presentation. Everybody can see the screen, right?
Yeah.
Okay. So I will just go through the overview of mud motors. Just I will go through the basics. Basically, mud motors are the positive displacement motors, which uses the hydraulic power from the flowing mud used to turn the drill bit without turning the entire drilling string. So basically, what we are doing is we are taking the hydraulic power from the mud and we are converting it to mechanical power, which is in turn turning the bit. So as you see in the schematic diagram which I put on the left side, basically the mud motor is just this is like a typical mud motor used by Schlumberger, which is very widely used, called power pack. So that's how it looks like. So I just go through section by section. I'll just go through small, and then I will on the second slide I will go for the some detail, just some basic details. So basically a mud motor, it has a power section, which is the top part just below the top sub, where the lower end, the lower end is the which has the transmission housing and the bearing housing. So the power section consists of a helical pair, rotor and stator. So basically you see here this is the rotor and stator inside. So this is where they, as I said before, the hydraulic power is converted into mechanical power, and this is where this then it goes down the string and down to the bit. So inside, this is one of the critical parts of it's one of the critical parts where the mud motor is totally dependent on. So inside this is how it looks like. If you see the below picture, it's outside there is a housing, inside there is a rotor and a stator. So so inside the housing, basically it's made up of rubber, which is called as elastoma. So the rubber can be of it can be hard rubber, depending on previously we used to have a cylindrical housing with rubber inside, but now things have been improved to increase the durability of the
Two
rotor and
minutes
stator.
left.
So
2 minutes left,
yes.
Sunil.
Okay. So I'll just go for the components of the mud motor. Basically, we have the power section, which I already told you has the housing, rotor, and stator. So if you are using a single lobe, these are the lobes which I have put the diagram here: 1:2, 3:4, 4:5, 7:8. So if you're using 1:2 lobe, you can achieve high speed during drilling and low torque. But if you are using a helical shape, this is a helical shape lobes, which can be 5:6, then you can achieve high torque and lower speed. So basically, whenever this rotor has like number of lobes, the rotor lobes always +1 than the stator lobes. So this is the transmission housing. Here we have the bent assembly, which you can bent housing where you can orientate shaft from the drive shaft. You convert the hydraulic force into the bit, and you can rotate the bit. So basically, you can have a good control when you are doing a directional well. You can do the orientation from the surface while drilling, and you can achieve a good ROP, and you can achieve a good ROP you can set your motor bent angle to 0 degrees, and also you can increase the RPM of the bit to raise the cutting capability. Even this has some drawback, like you can sometimes when you are drilling, you can have
1 minute left.
string which slack, because okay. So the issues with some of the issues which with positive displacement motor is you cannot have the full weight down the string you can have, because of sometimes cannot have a good shape. So you can have a string compression, you can have friction. Sometimes you can have an issue of string getting stuck bottom. So these are some, also you can have hole cleaning issues, because the cuttings cannot just come out. So these are some of the issues which we have. Otherwise, yeah, we can have a good help with for directional drilling with mud motors. That's it. Thank you.
Thank you, Sunil, for such nice information about mud motors and the mechanics of the rotation.
Thank you, sir.
You are welcome. You guys have any question for Sunil?
Yes, I do. Can I ask him, please?
Okay, go ahead.
Yes,
so he talked about the mud motor and the PDM, positive displacement motor. I wanted to ask what's more efficient in terms of transmitting the energy. Is it the turbine or the PDM?
I think the PDM is more better to use than the turbine, because with positive displacement, nowadays we have more better motors which can really work much with directional drilling. So I think for me, I would say PDM, positive displacement motors.
Thank you, then.
Okay, thank you, Sunil. We will move ahead.
You, sir.
You are welcome. Thank you for your time and your presentation. You are welcome. We will move to Abhishek Sen. The topic is wireline, the difference between wireline and MWD.
Hello, Mr. Wael.
Hello.
Myself, Abhishek. Yes, you can hear me?
Yeah.
Hello.
Go ahead.
Yeah, hello. Yes. Myself, Abhishek. I'm a consultant well said geologist, currently working for the Petronas.
Okay.
Yeah, my slide is very small, and it is just a general slide to differentiate between the wireline versus MWD. So wireline logging is the process of obtaining data after drilling of a section. On the other hand, the MWD, LWD is the process of acquiring real-time data while actual drilling for the faster decision making, like this geosteering. We have the faster decision with the use of advanced MWD tool. And wireline data can be affected by the mud invention due to the time constant between the tripping and other rig operations. And MWD, LWD takes less time after the passing of the drill, due to which it does not get affected by the mud invention. And now the wireline operations are less expensive than the MWD, LWD operations. And the logging while drilling is bigger, heavier, and tougher. That is suitable for every condition. It is quite common. Wireline logging is smaller, lighter, and delicate. That suffer problem with high deviation. And the LWD is more suitable for tough environment like deviated wells, unstable boreholes, and horizontal wells, where the wireline services are suitable for light conditions. And the power and communication in wireline logging are better than the LWD drilling, as it uses wires for the communication. However, with the introduction of wired pipe telemetry in LWD, it is possible to send the real-time data at higher speed. So it's a very short slide for me.
Thank you, Abhishek Sen, for this nice very summarized
It's a very
information.
summarized. It's a
Yeah.
very, I came to know that we have to
Okay.
present 1 or 2 slides. That's why I keep it very
Okay.
simple.
Okay.
I mean, my slide is not so fancy like other guys.
It's okay. Thank you for such sharing knowledge. You guys have any question? Okay, we will move forward for Mr. Basim Al-Ghul. He will speak about LWD versus MWD.
It's Bassam.
Bassam? Mr. Bassam.
Yes.
Okay, go ahead.
So I will share. So can you see my screen?
Yeah, very nice.
So my name is Bassam Al-Ghul. I have a BE in petroleum engineering from Phoenix University, Lebanon. I have few internships in both upstream and downstream industry, but I'm currently looking for a job if somebody can help me, in fact. So let's starting first. Okay. So if you can you still see my screen? Can you still see my screen?
Yeah, we see this guy.
Yeah. So the tool that this guy in the picture is holding to make sure that the wall is straight is the same tool used to know the well direction and inclination. Yes, the first MWD tool used to be a plumb bob. Can you imagine how time was lost in this process, especially with deviated well, and with $500,000 a drilling rig rate? This is a lot of money. Therefore, measure well drilling was invented to provide the real-time data for drillers and engineers to monitor the well track. So by definition, logging while drilling is generally terms used to describe the system and technique for gathering downhole data while drilling a well. A more specific definition is the acquisition of petrophysical data, like resistivity, porosity, sonic, gamma ray. Generally, logging while drilling offers the same measurement as wireline, some different zone or coverage. Generally, which refer to the acquisition and collection, report deviation, the acquisition and collection of drilling mechanism data like downhole torque, pressure, vibration, and the process of sending the data uphold in real time. So the main difference between LWD and MWD is the time that the results is brought to surface. So why not all the data are sent in real time? Let's have a look. So the most common way is to send the data uphole by generating a pressure pulse in the mud column that's being pumped down the drill string. There's a few ways, we're not getting into details, but the most these pulses are decoded into bits.
2 minutes
the most
left.
advanced one
2 minutes left.
can reach up to up to 24 bits per second. Commonly, it's 6 bits per second. The old methods used to max out at 1 or 2 bits per second. So the mud pulses are received by pressure transducer at surface and decoded into bits, which are broken to words or measurements. To put it into perspective, common measurement like GR, gamma ray, or density might take 8 bits. Annular pressure might take 16 bits. When you consider there might be 20 different measurements sent up and only 6 bits, you can see you can't get high density of all measurements. So logging scientists and engineers has to prioritize which data they need in this drilling to send now in real time. Thus, MWD and logging while drilling should focus on the essential for monitoring and improving drill position. So a quick example is very interesting example I saw. So if we're waiting for
1 minute left.
Yes. So why we use logging while drilling if we're already waiting for the tripping out? So this example is very interesting because logging while drilling is done within 1 to 4 hours of drilling, while wireline is 1 to 4 days. So in this example, you can see the invasion of water from the resistivity invasion of water is not, when comparing logging while drilling with wireline logging, the invasion of water, or like a very resistive mud, the invasion is not yet complete when deviated. So there's this deep invasion up in the 3000 and the 3050 can be missed out, and missing millions of barrels by just not measuring the right resistivity. That's why the comparing or the invasion correction chart are now becoming available to address this issue. So we avoided missing millions of barrels by just what can I say, the logging while drilling. And thank you.
Thank you, Bassam Al-Ghul, for this nice presentation. You guys have any question for Bassam?
So
Okay.
Too fast.
Okay, Bassam, thank you for the presentation. We will move forward to our next speaker, Sheriff Saida, about
Hello?
Hello, yeah, hello. The topic is RSS. Go ahead.
Can you hear me?
Yeah, we hear you.
Okay, I'm gonna share my screen now.
Go ahead. We are waiting.
Okay. Okay, good evening, everyone. Hello?
Hello? Continue.
Hello?
Yeah, we hear you.
Good evening, everyone. My name is Sheikh. Okay, great. Wait a second, wait a second. Good evening, everyone. My name is Shirif Saida, a drilling engineering student from Algeria, and I'm gonna present the Rotary Servo system, or what we call the RSS. First of all, what is it? It is a form of a drilling technology used for geosteering. And now, why do we need it? We need it to solve the problem occurring when using the sliding method, such like poor hole cleaning, low ROP, stuck pipes, and the inability to slide properly, and all the other problems that could occur when we leave the string static in the hole. Now let's move to the part to how it works. The RSS system is controlled from the surface by changing the flow rate between high and low. For example, we send 10 seconds of high flow, then another 5 seconds of low flow, then another 5 seconds of high flow. For example, it's like a code. When this flow arrives to the RSS tool, when this flow arrives to the RSS tool, it will translate it and change the drilling parameters according to it. Now, how it's gonna change it? As you see in the pictures, in the slide, there is a little pad on the side. It will activate it and it will push the BHA to the desired direction with the desired steering ratio. Now, how are we gonna know that it's doing it right? The RSS tool will send signal to the MW tools. It is more like frames. To the WD tools, explaining the parameters it is working on and all the conditions.
Sheriff, you have 2 minutes left.
WD will send it to us using Okay, and the MWD will make sure that the right execution of the command is done. And thank you very much. If you have any questions, I'm here.
Saida, Maybe someone else will
Anna,
actually
yes.
also answer this question. What's the impact of the RSS when there is a sliding? For example, if you have a gamma ray density tool.
I didn't understand the question. Can you please repeat it?
What's the impact on the density of the gamma ray images when there is a sliding?
Okay, so he mean sliding will affect the imaging. So he is asking about the impact of a sliding if we have density imaging. This is your question.
I have no.
Yeah.
I didn't do research about it, so I can't answer you.
Okay, maybe
I have no
okay.
idea about it.
Can I jump in while regarding to this question?
Okay, go ahead, Said.
Yes, please.
So since the most important for this, it is a very big advantage for RSS, which is rotary steerable assembly. I guess the colleague here was speaking about push the bit system. Whatever it is, push the bit system or point the bit system, it's a very good advantage for RSS. There is always you have RPM. There is no sliding. This is the idea behind. This is the idea behind the RSS. You always have RPM, so there is no impact for the image. I am sure the question is regarding to you need the RPM for image, right?
Yes.
So here, unlike the motors you have a stop RPM. You have to stop RPM and start sliding in the desired direction. But for RSS, you don't have to do it. You just send an command, and the tool is executing steering at the desired direction. So you always have RPM, so no impact for the image.
Thank you.
So it's better for the image.
So much.
Okay, rotation is mandatory for the image, and in some situation, if we don't have rotation, we have to stop and rotate to get the image. They call it reaming back, to get the image, and then they drill, and then they stop. They ream back to get the image, and then they drill, and then they ream back. So just rotating without drilling to get the image. So this is answer your question. Okay, we will move forward to thank you, Sheriff. We will move forward.
Thank you so much.
You're welcome. We will move forward to the next speaker, Ayuti. He will talk about real-time monitoring. Go ahead.
Thank you.
You're welcome.
I shared my screen. Is it visible?
Yes.
Hi, I am a PhD research fellow at Indian Statistical Institute, and before that I worked 2 years in Kane, India as a geologist, and I was assigned to a team which had an ongoing drilling campaign. So, and I was assigned for real-time monitoring, and that's why I chose the topic. Now, real-time monitoring is very important, integral part of delivering a successfully well. Even if we are drilling an exploratory well, or we are drilling a horizontal well, or we are drilling a vertical and deviated well in a field where we already have a lot of drilling data. Because I will be talking on the geologic aspect of real-time monitoring, because I'm a geologist, and the geological uncertainty is high. So every time we build development. So the generalized flow before real-time monitoring, we need to pre-drill that encompasses finding well plan, getting a well plan from the drilling operator if we have a drilling partner. In our case, it was Halliburton, and we generally get the well plan. We give them the subsurface target, and we get the well plan in return. And then we, as a geologist, we load that and we check whether it's meeting our subsurface criteria. And then with the most updated available model, we well plan and we make the geological prognosis. Prognosis is a very important document. It is with the geologists, the well site geologists, we monitoring it from the office, as well as it stays the drilling person, the drilling team, drilling engineer. It generally has the formations and the tops of the formation at what TVDSS or what MD we encountering that, and any shift. It also has the prognose TD. Any shift from the given prognose depths of the formation tops or the TD is a real-time call. How we will be continuing with the drilling of that well. Next, this is the generalized flow for we do it third-party port. We have all the well data, offset well data, the models, the petrol project, and
2 minutes. 2 minutes. 2 minutes left.
Okay. Okay. Then a third-party portal from the real-time monitoring with petrol, we actually enter or connect with the third-party portal. It has been already shown. Has already shown in one of the patients before, and it's very important to enter from third-party portal, and because we will get this acronym of different logs that during the drilling third-party portal has streaming, and knowing the acronym of logs is very important.
Okay, you guys all missed the connection from Ayuti?
Yes, we did.
Yeah, I think.
Okay, maybe she faced some emergency connection issue. We will.
I'm back. I'm back. Can I start?
Okay, because you have.
I will just take.
Okay, you have just 1 minute.
Yeah. Okay. So after that, wait a bit.
So now can please go to the conclusion, because we run out of time. Ayuti.
See the screen?
Because you are suffering from a connection issue.
Hi. Can you hear me?
Yeah, please jump to the conclusion.
Just to show last slide actually.
Okay, go ahead.
Can I come 1 minute after one presentation? Can you please excuse?
Okay, we can move forward. Please allow us,
hello,
Ayuti, please allow us now to move forward to the next speaker.
Screen?
And then I'll give you a chance at the end of the presentation. If anybody has a question in your topic, you will get the stage again to get in. Okay.
Oh, this is my last slide. Can you see it actually?
No, because you have an issue with your connection.
Okay.
Believe يعني if. Okay, try now again. Try. Just try.
Fine. Can you see the slide?
Yeah, we see it. Go ahead.
Yeah. So this is an example for the real-time monitoring challenge which we had. This was the plan, the left the well plan, and we thought that we will be entering after the shale will be entering the reservoir, but due to they wanted to drop the angle as they after reaching the reservoir, and we have tagged the fault initially in other 5 wells as well. So we were confident about the fault positioning, but as we dropped the angle and diverted it a bit from the given well plan, we entered the shale of the hanging wall. So we could identify this problem in time, and we can do a sidetrack and go back to our formation again. And this was one of the most important real-time challenges that I faced during my tenure at that oil and gas company. Also, sometimes real-time monitoring is important for taking TD decisions. If the oil column drilled is less than predicted, then we will TD at the sand only, safe from opening the water zone.
We run out of time because I still have 15 speaker.
Thanks. That will be all.
Yeah, I really appreciate your time and your knowledge sharing. Thank you. We don't have time for a question. We will move forward to the next speaker, Mr. William. He will talk about geological changes while drilling.
Hello, can you hear me?
Yeah, we hear you.
Okay, great. I'll start my speech. Okay, can you see my screen?
Yes.
I can't go with slideshow. I don't know why. Slideshow? Okay, great. Good evening, everyone. You hear me?
Yeah, we hear you.
Okay, great. Good evening to you all. Thank you, Engineer Wael, for this opportunity. And I would like to thank you all for sharing and explaining all these interesting topics. I'm William Al-Sayed. I'm a fresh graduate. I have a master's degree in petroleum geoscience from the Lebanese University and a master's degree in petroleum engineering from the University of Aberdeen. We're gonna go quickly through geological changes encountered while drilling. As you see in the 2 pictures to the right, the best way to understand geology is via outcrops. These are an example of the heterogeneity of the layers we might encounter while drilling, both in terms of the composition and the geometry, as we can see these beautiful faults from release, actually. Okay, geology and drilling. As we can see here in this schematic, we have several hydrocarbon accumulations trapped in different ways: fault, anticline, stratigraphic, or because of the presence of salt domes. In order, we can see the drilling rig also. In order to reach our reservoir, we have to go through a lot of layers, different layers. We have to drill to get there. We have, as you see, we have clays, we have limestone, we have shale, we have sandstone, which is the reservoir in this case, and also we might encounter salt. These different layers have different characteristics. A drilling engineer must consider, like one of the most important characteristics is the formation hardness. So while drilling, we'll encounter several formations. Each formation has a different hardness. It ranges from soft to medium soft formation like shale, clay, limestone and sands, medium hard to hard formation like hard limestone, sandstone and dolomite, hard and abrasive formation not shown in the schematic like granite, basalt, quartzite and chert. So now, based on these expected formation, on the stratigraphy we had, or from the wells drilled beside our field, next to our field, we must know which formations we are expecting to have. So we have to choose our drilling bit based on that. We have the roller cone, the fixed cutter bits, PDC, which are mostly used to drill soft to medium hard formations we discussed in the previous slide. And also we have the Chimera hybrid bit, which is actually a mix of the roller cone and the fixed cutter bits. It's actually a Baker Hughes tool. And also we have the diamond bit, which are more expensive, but are mainly used for hard formation.
You have 2 minutes left.
Okay, great. Similarly, a drilling engineer must take in consideration, mud engineer, drilling engineer, or operation engineer must take in consideration mud weights and mud additives that must be considered for different and each formations to ensure a safe drilling. Last but not least, let's talk about geology and directional drilling. Directional drilling is applied in several cases, but these 3 cases are mainly because of the geology of our field. So it's applied for salt domes because we can't drill into the salt. We have to drill around it, because drilling through salt can cause large washouts, lost circulations, and corrosion. Also in faults, it's important to use directional drilling, as it's important to enter the fault perpendicular, to enter the faulting zone perpendicular to it, to avoid sliding. And also it's applicable for layered reservoir, laminated reservoir, to reach all the pay zone. So this is just a simple presentation. Thank you very much.
Thank you, William, for this nice presentation about geological changes while drilling. Any question for him?
Thank you.
You're welcome.
Thank you.
Okay, we will move forward to the next speaker, Mr. Salahuddin. He will talk about tool face. Go ahead. Salahuddin. William, can you?
Hello again. Do you hear me?
Yeah, we hear you. Okay, you need me to share your presentation, right?
No.
Salah.
Okay, Mr. Wael, I have sent you my presentation.
Okay, just a second.
Could you please share it?
Yeah, just a second.
Thank you very much. I couldn't share it because I'm using my phone and it's a bit unsuitable. Hello everyone, so this is Salahuddin from Algeria, drilling engineer and wireline logging operator. I will talk to you about the tool face. This is a bit straightforward presentation. I would like to take a chance to thank Mr. Wael for the initiative, and thank specifically Rotary for sponsoring this course. So I will talk first about the two types of tool faces. So we usually have a combination of two tool faces, gravity one and the magnetic tool face. One is working according to the horizontal plane, and the gravity one works to the perpendicular plane. So the gravity tool face usually uses accelerometers, while the magnetic one uses magnetometers. So what is tool face? It indicates it's the angle between the rotor, the motor axis, and the plane we are drilling in. It indicates the direction in which the drilling motor or rotary steerable is pointing the bit in order to steer the well directly. Could you please put the definition? Just click. So to put it simply, It is defined as the angle between the bent sub, which is the responsible for the directional, and the vertical plane. Next slide, please. So the magnetic tool face is the angle between the tool reference axis and the magnetic north in a horizontal plane. We usually use it when the inclination is less than 5 to 8 degrees, while we use the gravity tool face while we have more inclination, above 5 to 8 degrees. So the angle between the tool reference axis and the center of gravity in a vertical plane is what we call gravity tool face. In the next slide, we will see a physical representation of what we usually see when we use the combination. Could you please go to the next slide? Okay, it's uploading. So this is what we have in our box when we are steering from above. We have the azimuth, as you can see down, the inclination. The inclination here is 6 degrees, so it's between the range of 5 to 8 degrees. We are using then the magnetic one. The green line shows the current.
You have 2 minutes left.
Okay, no problem. I'm almost finished. So while the blue to green line shows shows the magnetic north, and that's why we should adjust our angle to go and to steer to that direction. So thank you very much. Maybe the directional directors will shed some more lights about this in the next slides or in the questions. Thank you very much for your attention. I'm available for answering. Okay.
Thank you, Salah, for this presentation. Anyone has a question for Salah? Okay, we will move to, thank you, Salah. We will move forward to Ash Rana. She will talk about Lwd Density Image. Let me firstly stop sharing my presentation. Okay. Ash Rana is here?
Yeah.
Okay,
yes.
go ahead.
Just a minute, please. Let me just share my screen. Bear with me. Right, so my name is Ash Rana. I work for a company called Emerson. They normally deal in automation, valve automation solutions. So they also got some software and development section, both Paradigm and Rockstar. So I work with one of the team in reservoir characterization. So I don't have so much experience in a service company, a little bit experience, but mostly I work in a operator as a petrophysicist. So I'll try to share some of the knowledge which I have really earned over the couple of years. Just so you know that the data which I'm using is actually, if someone wants it, it's available on Valvo data. It's a Norway field, so I can send you all the raw and process data is available online on one of the Equinor portal. So the Lwd density image, why I choose this is the reason why I feel that this is the best image so far we have seen in geosteering. We have also quadrant image data, and we have also the 8 and the 16 sectors. When I say 8 and 16 sector, you can also say 8-bit or 16-bit image. So what it is that in 16 sectors, as you can actually see here, or this should be actually here. They actually divided this borehole in 360 degree, and this sector is 22.5 degree. So as the tool is going down, it is actually azimuthally moving around in the hole, and it is actually in each sector, it's actually acquiring the image and pulsing up the image up in real time, and also is stored in the tool, what we say memory data set. What actually I have learned that the 4-bit, 8-bit, and 16-bit image or 16 sector, there is actually a resolution difference. For example, in Weatherford, they have azimuthal gamma ray, which is 4 sector 4-bit, and we have also the Schlumberger one, which is Echoscope, or also Weatherford one, the 16 sector AZD, azimuthal density tool, 16 sector. The resolution is quite high, and when you are geosteering or you are doing a geosteering job, it really helps actually when you process the data, especially when you calculate the depths. So
you have 2 minutes.
Okay. One of the things which we have is that you have actually in 3D, this is the fracture plane, and when you unwrap it, and then you get this the north, and the direction. So this one is the sinusoid actually, which we actually need it to compute the depth, and this is the apparent depth. And once we calculate, we can actually convert this apparent to the true depth. And this is the horizontal one, the top of hole, this is the north-north. Now, in here, what you actually see, the 16 sectors, the density curves, this is the raw data coming in. And what we do, we combine it, and then we actually create an image, orientate that image. And then after that, we enhance the resolution. We actually further process that. We create the static normalization and the dynamic. So what we do then in static, we take the min and max of the top and bottom. And in dynamic, we actually take the 10-meter window to enhance the resolution of the image. Now in here, what you actually see this...
you have 1 minute.
Okay. Static and dynamic image, and it's very nicely actually, you can certainly see that the beddings, this is mainly actually, we have seen that the beddings are actually picked up there. I could not actually show the other features. For example, we could also pick the fault, the fractures in here. So yeah, so the one of the thing is that the Lwd petrophysicist, which actually is working closely with the geosteering geologist, you are actually in real time picking the depths, which actually tells you that the structural trend of the formation. Now, the advantages which I mentioned here, generally fair to good resolution, 16 sector in real time or memory, useful application, very useful application during geosteering. And disadvantage is no image in sliding. So that's what actually I just recap this one. Now, the software, I also promised that I would actually talk a little bit about the software. So the Weatherford is actually using, I'm not sure if you know, and still they're using a log XD. I don't know about the Schlumberger one, what they're actually using. But the operators, they are using different softwares. For example, one of the software which I actually work, not so much in geosteering, but the image interpretation and all this is actually Geolog. So inside Geolog, they got also the geosteering module, which can also stream in the real-time data as well. So which means you can actually directly connect to the VirtuML server while it is being built.
Mr. Ash, Rana, actually we run out of time. thank you for your presentation. Such nice talk about the image. We have a question regarding your topic about the resolution and depth of investigation of this tool, the density tool, the density image tool.
Sorry, say again.
There is a question about the resolution. What are the resolution and depths of penetration of LWD density image tool?
So this
is generic question, but you can very generic.
Echoscope image. So what I can recall, I think it is around 15 centimeter the resolution. This one.
Okay, it's a few inches here. Okay, thank you, Mr. Ash Rana, for your nice presentation. Stop sharing your screen, and we will move forward to the next speaker, Farid Magdi. He will talk about geosteering versus directional drilling. This is a good topic as well. There was many questions yesterday about this topic. Farid. Farid. افتح المايك يا فريد. Farid?
Hello?
Yeah. Go ahead.
Okay. I'm so sorry for the technical issues started with.
It's okay. Okay, you can stop sharing until you find your.
Well, it's just.
Okay.
3 seconds or something. I'm so sorry.
Okay.
I was so much concentrating with the session that I didn't prepare it in the background, so I'm so sorry.
It's okay, no issue. Take your time.
Well, first thing, checking. Do anyone do not see the screen? Hello, is the screen okay?
Okay.
Yeah, it's okay.
Okay, very much, thank you. First thing of all, I hope you're all having a good evening wherever you are. Our topic today is directional drilling versus geosteering. We'll have some quick remarks on it, but before that, please let me have a 1-minute video introducing myself from a virtual interview I did lately. If I do not take this chance to try to make up more connections, that would be very bad. So I would like to start with who am I, and I hope the voice is going to be reaching you.
My name is Farid Magdi, fourth level student by the Faculty of Science, Alexandria University, studying petroleum geology. First on my class, with 3.9 out of 4 CGPA, considered excellent with honor. A former trainee with a bad sheet, BB, Canada, farmer oil, Arab contractors.
We can't hear you clearly.
Aside from having the chance to get a...
Is it only me?
The voice isn't reaching you?
No.
Yeah, maybe because of the streaming, Farid. So we apologize for this. You can move forward to the topic because the graphics will make the stuff more heavier.
Yeah. Okay. Never mind. But please, can I just give it one more try? If it's
okay,
not giving you any voice,
you can put the link for this nice video about your profile in the group.
Okay, never mind.
Okay, share it with
So
us in the
anyway,
WhatsApp group.
Okay. So summarizing what was supposed to be said, I'm a first level student by the Faculty of Science studying petroleum geology, being the first in my class, and I'm trying to, as you can see, maintain every possible chance to get any knowledge possible from wherever the source is, and also to maintain as much communications as I can before graduating, as we can know that the communication is a very critical part in the petroleum industry, and I cannot really express how much I am honored to be in this group. So going forward to the directional drilling part.
We have a black screen. Okay.
Speaking of directional drilling, it's more like a general term when it's versus geosteering. You know that the directional drilling, as Dr. Wael has said yesterday, is about finding a target and trying to maintain the best way to it, but using only the original and crude techniques where we ever known for the very past years. The reasons behind doing it, you can know for either having like relief wells, a lot of production, either having some problems with salt domes or fault controlling techniques. Getting over to all the possible trajectories we know about the directional drilling. These are the main three, very well known. We did talk about them, and then we move to the possible techniques of drilling. You can either do it for a rotary technique using the pendulums, stabilized, or fulcrum principles using stabilizers, or either you go for the motors. Mud motors in specific mentioning here. And after that, you can see the rotary steering set. But I know this video, the problem with the voice is still a major issue. But I guess the graphics would be okay if you give me a 1 minute of your time to see.
Actually, both the voice and the graphics. Let us check.
Geopilot rotary steerable system.
Is it working now?
As part of the pilot fleet of automated drilling systems, the Geopilot is the industry's most proven point-to-the-bit rotary steerable system.
Unfortunately, Farid, there is an issue with the graphics. Sorry for that.
So is this due to the internet connection, or is it due to the Zoom? I'm kind of new to this app, so
no. This is a common issue now, especially in Egypt nowadays. Okay, move for you can move forward.
So I'm so sorry about it. I should have been preparing for it, knowing the local issues we have. So going over to the geosteering part. This is the most interesting thing, as it's actually the mainstream thing about this course.
Yeah, you have 2 minutes left. Farid, you have 2 minutes left.
Okay. In comparison to directional drilling, it's more likely a quality assurance approach, trying to get the most probable accuracy you have having mainly the same drilling string, but adding to it a lot better like plugin tools and other informative tools to give you the best path possible and best knowledge, integrating everything together to have the best decision on how to be maintaining your path through the target, inside the target. So as you can see, having geological models, there's actually a very much probable errors as in the red path, because the probable actual path can be very much different from it.
One minute.
And we stay in the pay zone, and we also violate model errors. So, okay. Turning over to the errors we mentioned before about geological position changes and structural uncertainty. You mentioned it yesterday. And then going for the downhole tool, as we said, there's MWD, there's density neutron LWD, and resistivity and power drive. Our info, we get it from the cuttings, from also paleontological techniques, and we also, as we said, from MWD we get the drilling mechanics and survey measurements, while from the LWD we get the formation evaluation part. As we know, 3 important points. The first one is the model update, and the second is the determination, and after that, the distance to the boundary technique, the remote detection tools.
Last slide, Farid.
Well, these slides I won't be given any news. I'm just referring to what we said yesterday. We got the model update in this video, and we got the depth change through this cutting down and cutting up smiley face and sad face.
Okay, thank you, Farid. Thank you for such review. Thank you, Farid, for such review for geosteering and directional drilling